Hello everyone, I am Pushpita Chandra. I am a PhD student under IIT Delhi and University of Queensland joint PhD program currently in IIT Delhi. So I'm the TA for this course, Introduction to Lasers and Laser Systems. So let's begin today's class. Today is week 8 and our topic of discussion is molecular spectroscopy, which we want to discuss because we want to understand how molecular spectra and molecular level works and how it helps in carbon dioxide laser to generate its lasing action. So molecular spectra. So basically in molecular spectra we get from molecules, which is an obvious thing. And so the molecular spectra is consisting of electronic energy level, vibrational or electronic spectrum. So where you see spectrum has electronic spectrum, vibrational spectrum, and rotational spectrum. Okay. So basically, we will get electronic spectra when there is a split in electronic energy. So there will be a transition between from one electronic energy level to another electronic energy level. Vibrational spectra we will get when there is a transition between one electronic vibrational spectra between another one vibrational energy level to another vibrational energy level, and basically, and we will get rotational spectrum when there is a transition between one rotational energy level to another. And later we will get to see that there are some quantization rules, so that enables that for any vibrational rotational spectra, delta nu has to be plus minus 1. 0 is not possible. So there is not possible to get a rotational, like theoretically that is possible from same vibrational energy level. There will get rotational spectra between due to transition between two different rotational energy level within same vibrational level, but this quantization rules made it forbidden. Uh, why these rules forbidden and all those things? Because basically those lines are so like so faint, and they are not probable that we don't get this line. And how much this is comparable? The vibrational energy is basically 1/100th of electronic energy, and rotational, that is almost rotational energy levels are almost 1/100th of vibrational energy level. So basically, this rotational spectra that lies in microwave region. So some molecules are microwave inactive because of this, because those molecules doesn't uh, produce rotational energy levels. So some of the uh, example are oxygen, nitrogen. They are linear, and they do rotate, but they don't have any dipole moment change. So they kind of give no rotational spectrum. Hence, microwave inactive. And why they don't have a dipole moment? Because they are highly symmetric. So we are discussing this molecular spectroscopy because we want to see the working of molecular lasers. So what are the advantages of molecular lasers? That the lasing energy level is close to the ground level. Due to that, we have very high quantum efficiency, and B, the emission is in infrared region. Mid, near, and far. So to get an infrared laser, we need to work in the molecular lasing, molecular energy levels area. So we will start with some basics of molecular spectroscopy. So we are considering a very simple molecule which is made of two atoms, A and B. And in general, we assume that the bond between the element A and B it is generally elastic in nature. So they are actually either joined by they act like that they joined by a split. So it's equivalent picture when we get to CM frame is like this, that the one mass of weight mu is connected to the spring from a wall, and the mu is basically A B MA plus MB. So this is center of hemisphere. So the molecular vibration is essentially a periodic motion of its constituent atoms, and the principle of conservation of linear momentum precludes any motion of the center of mass. And similar to electronic energy levels, the vibrational energy levels are also quantized. So the polypop dropped. So basically, the vibrational energy level has been given like mu plus half into h omega, or for the sake of simplicity, it was h omega naught. And omega naught is basically 1 by 2 pi root over k by mu. Mu is the reduced mass, which is ma in p by ma plus nb. And mu can be from 0, 1, 2, 3, and so on and so forth. So if when I put it that 1 by 2 pi and more less, so that becomes mu plus half h cut root over k by mu. So when the gap between two energy levels, we can compute that is mu plus 1 h cut root over k by mu naught minus mu plus half h cut root over k. So that is h. So we see that the distance between two vibrational energy levels are always constant, but that doesn't happen in particular. So we see that it's independent of, so the h mu naught basically h cut root over k by mu. So there is no number mu. It is independent of mu, it seems like that. But when the vibrational energy levels, the nu is very high, there at it there is a term like this is no longer h nu not nu plus half only. There is a term psi e h nu not nu plus half whole square. So due to this term, the distance between these two energy levels doesn't keep constant when mu is very large. And this psi e is a constant which has a very small value, 0.001. So when it's being multiplied by a small number, it remains small. But when this number gets bigger, it is not that small anymore. So for low-lying vibrational level, this is true that difference between two energy levels are always independent of number nu, but for high-lying energy level, that is not true. So basically for each electronic energy level, so if we say that it is a zero energy level, so the vibrational energy levels start like this. So this is, if you say n is equal to 1, that electronic energy level 1, according to we will get, and this is equal for nu is equal to 0. From this equation, you can see that even nu is equal to 0, that is no free energy level, right? So that is the case, and if therefore for n is equal to 1, that this denote one electronic state and this denote another electronic energy level, and that electronic energy level is also split in different vibrational order. So in principle, if a transition happens from 3 to 1 or 3 to 0, we will get a lessing action. So that's why you can see that for electronic transition, you can see that we need to have a transition from this excited, instead of N1 and 2, we can say this is ground electronic state, and this is basically electronic excited state. Okay, so this is a lacing action. This can provide a lacing action between the transition between two vibrational energy levels. But if we want a lacing action, so this vibrational energy level only we will have only in the molecules, not in the atoms. In atoms, the transition has to be in the from one excited state to ground state. So you can see that basically the lacing levels are very close to the ground level here. And that is why the molecular lasers have high quantum efficiency. But molecule doesn't only have vibrational energy or vibrational spectra, as I mentioned earlier, that it also has rotational spectra. So they actually rotate with vibration, and this rotational energy G levels are also quantized. So after calculation, the quantized rotational energy levels are denoted by, we got the calculation, J into J plus 1, 8 square, 8 pi square I. And I is basically mu per square. Mu is reduced to mass, you all know that. And I is moment of inertia. And instead of writing all those things, you can write V into J plus 1. And here J starts from 0. And you can say that in J, the lowest rotational energy level can be 0, but vibrational energy level cannot be 0. And P is equal to generally H square by 8 pi square I. This is a kind of constant, or J is here the rotational quantum. Here mu, that mu is vibrational quantum. And the distance between two energy level of the spacing, can see that mu J plus 1 to J plus 2 we have minus J into Bj into J plus 1. After all the calculations here, that we can, that it is J plus 2 minus J, that is 2Bj plus 2. So from this equation we can see that the spacing is not equal. So for J equal to 0, if it is here, this J equal to 1. So first difference is 2B, then for J equal to 2, that transition is 4B. For J is equal to 3, this is 6B. So when a molecule transit from J is equal to 1 to J is equal to 0, it emits energy 2B. From it transit from J to J1, it emits 4B, 6B. But see that the difference between this 4B to B is 2B, 4B, 6B is 2B. That is constant. But the energy spacing is not constant. And as I have already mentioned, that rotational energy is 100th time of vibrational energy. So the energy required is so small that a typical gaseous sample at the ambient temperature, all the molecules are at a different excited rotational state, even in the ground vibrational state. Now we have seen the rotational state, the vibrational state. So this is the combine of rotational vibrational state. And why we need to combine both of them? As I mentioned, that the for rotational energy levels or the rotation of the molecules, the energy requires so small that even in normal temperature, all the molecules are different rotational energy levels. So there is no pure there is no possibility of getting pure vibrational spectrum. So we always have rotational vibrational spectrum. So this is the energy splitting for ground vibrational level for which the quantum number is nu is equal to 0, and this is the splitting of the first excited vibration state for which nu is equal to 1, and for nu equal to 0 there is z is equal to 0, 0, 1, j2, j3, j4 for nu 1 also. And as I mentioned, that from where we will get pure vibrational spectrum, that not obviously that for oxygen, for nitrogen we will get pure vibrational spectrum at normal temperature. Because even with temperature and energy, we can induce dipole moment in these molecules. Some of the liquids also show pure vibration spectra because they cannot rotate for different reasons. So for the transition happen, there are some selection rules. So these selections rules show that which transitions will be most probable, at all probable or not. So the selection rules are delta nu has to be plus minus 1 and delta j is 0 or plus minus 1. It cannot be plus minus 2 and all those things because that are not probable. So when delta j is equal to minus 1, that delta nu plus minus 1 means the transition has to be two different vibrational level. They can be in the same electronic level, but two vibrational level, but they cannot be in the same vibrational level. Two different vibrational level. So they are basically absorption, emission also follows the same. So here it was showing absorption. So when they have energy, they will absorb such quanta of energy that they will jump from one vibrational level to another vibrational level, and delta J can be 0, even 0 for this branch of thing. It transition from J0 to J0. But here it transition from J4 to J3. It can also go up to J5 also. So from J4, it can go to J3, J4, and J5. It has not been shown here. We can take J3, that here it's showing that J3 can go to J2, J3 also go to J3, and J3 also go to J4. Okay. So when delta J is -1, they are called, the transition are called P-brush transitions. So J to J -1. When J to J, that means delta J is equal to 0, that is Q-branch transition. And delta J, when they go to J plus 1, they are basically R-brush transition. So this is the frequency. This transition corresponds to this frequency. This transition corresponds to this frequency. So you can see that if the transition between J4 to J3 has lower frequency than the transition between J1 to J0. So you need to remember also that which transition lies where in the frequency band. So it's easy to remember that R branch plus 1, it will have higher frequency, and P branch will be lower frequency, Q will be in between. But in this frequency also, where there is like from lower J, their transition will have higher frequency. And these transitions, this vibrational, like from low rotational vibrational or low vibrational energy spectrum, lies in infrared region. So for infrared region, we needed to go to the energy spacing should be small from the atomic electronic transition, and that's why for infrared we need a molecular spectroscopy, not molecular spectroscopy, molecular laser, basically. So carbon dioxide laser is a molecular laser, and it can give you in infrared region transition, and it is a very fast molecular gas laser. And at low pressure, it can operate in a continuous mode. Or CW mode, and the energy can produce from watts to tens of thousands of watts. At high pressure, it operates on pulse mode, and the energy is generally in gigawatt. And it generates light between 9 to 11 micrometer. And when it is working in CW mode, so it is very easily used as a surgical tool. And using carbon dioxide laser on a like fingertip of some surgical tool, we can do the blood lossless actually surgery. It can also be used in like metal, but metals have very high friction at this wavelength, between 9 to 11 micrometer. So we need a high power laser, but at that wavelength, our body tissue, water, everything absorbs the energy so well. So we can like do the surgery with this carbon dioxide laser. And it also, like as I mentioned, that it can work as a CW mode and the pulse mode. It has high quantum efficiency. It works in both mode with adjustable pressure, low and high pressure. It has high repetition rate. Wide tunability. Readily achievable. Achievable. Spectral emission. So carbon dioxide molecule have 3 vibrational modes. That I have mentioned earlier in the class, also in 6 tutorial. What are they? They are the symmetric mode. Which are not is a mu. So what happened? This is carbon dioxide, carbon. This is oxygen here. This is oxygen. So in the first half of the vibration, the oxygen molecules moving towards the carbon atom is stationary, then the oxygen atoms moves symmetrically towards it, and they during the next half cycle they move opposite to it. So basically they are vibrating like this. But at the same time, when both are both oxygen molecule go towards the carbon molecule at the same time and go back opposite of that at the same time. That is symmetric mode. There is a bending mode. Which is nu2. What happened? That at first of the vibration, carbon atom goes upwards and they go downwards. The second half, carbon goes downwards and they go upwards. So asymmetric mode. So here the distance is asymmetric. Actually, what happened? In one half cycle, one carbon dioxide, carbon and oxide bond is stretched, like this bond is stretched, and this is squeezed. And this in the second half, what happened? This bond is stretched, and this is squeezed. That is called asymmetric vibration. And in general, all three modes are present in carbon dioxide vibration. So the energy, and another thing is that the energy required to excite one quantum of vibration is less for the bending mode. For bending, the energy is less. And for asymmetry mode, we can see that one bond has to be squeezed and another has to be like, for conservation of momentum, another has to be relaxed. This is the energy required is maximum. And for symmetric mode, the energy is in medium. But for symmetric mode, vibration, quantum energy is twice of vibrational bending mode vibration. So that much energy is required. And each mode has been denoted by this nomenclature, mu1, 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 mu2, mu3. So 100 represents that it is in a symmetric vibration mode, there is no bending, no asymmetry. And 010 denotes that there is only bending, and 001 there is asymmetry. So as I mentioned that symmetry mode vibration quantum energy is twice of the bending mode vibration. So basically 100 and 020 are at the same position. And the ground energy level will be denoted by 000. So the first excited state in the asymmetric vibration mode, that is 001, serve as the upper lacing level, and 100 and 020, which I have said that 100 and 020 are almost at the same level. They will operate as like a lower lacing level. So when the transition happens between the 001 to 020 and 001 to 100, we will get energy above 9.6 micrometer and 10.6 micrometer. And some selection rules, this is a vibrational mode and these are rotational mode. So some selection rule, 001 will not have even rotational modes, and 100 and 002 will not have odd rotation. And this shows the probability of where the molecule resides mostly. So for J is equal to 17 and 15, molecule will reside mostly, or here 18 to 16. So the transition is most probably from 17 to 18, or 19 to 18, or 15 to 18, so on and so forth, like in that region. But there also be transition like here when it doesn't have even mode and it doesn't have odd mode, those J is equal to 0 branch, which is Q branch, we will not get that, but we'll get the P and R branch. Q branch. So we can have from J11 to J10 or J12, but their probability is very fit. So previously, when only carbon dioxide gas was used, what happened that carbon dioxide molecule, which is at 000 level, it got collided with electron. So that goes to carbon dioxide 001 level, and electron has less kinetic energy at that collision. But at the same collision, it can go up to 100 and 020 level also. And this is serving as our lower energizing level. From that, the molecules go to 010 or for 000 due to rapid vibration relaxation or vibration transition relaxation. So they are not lasing. When the molecules which go up to 100 or 020 after the collision with electron, they cannot lase. So the number of molecules we want to go up to 001 is already less. So the output is not that good. So to enhance the output, we need to confirm that every molecule go to at least 001 level. For that, we introduced, not we, the scientists introduced nitrogen gas. So nitrogen gas, as I have mentioned, that is a very linear symmetric molecule. Carbon dioxide is also linear, but it only has one vibration element. So for nitrogen, nu is equal to 1. They don't have nu 1, nu 2, nu 3, only 1 nu. So nu is equal to 1 is almost at equal of 001 level. So what happened that this nitrogen and carbon dioxide gas are mixed appropriately, and with the electron they collide, and obviously those some carbon dioxide gas goes up to 001, some goes to 100, 020, but there is also nitrogen, so all nitrogen gas goes up to this level, and after nu is equal to 1 nitrogen collides to the ground level of carbon dioxide molecule, and they are now at 001 level. So now more carbon dioxide molecule can go up to 001. So what happens? As N2 is equal to 0 plus kinetic energy into 1 plus electron reduced kinetic energy. Now they transfer the energy. Is equal to 1 plus carbon dioxide 0 we go to mean 0 plus carbon dioxide 0. Now this nitrogen is again free to go to nu is equal to 1 level and transfer the carbon dioxide the energy, and this carbon dioxide molecule has 001 will be in 001 level. So this nitrogen molecule can again excite another carbon dioxide. So another carbon dioxide molecule. So for that carbon dioxide laser in the mixture, then nitrogen will be in like in the same proportion. So as I have mentioned that it is on spectroscopic levels, all those there is no presence of mutational levels with even quantum number in the 001 level, and what quantum number in both the 100 and 020 levels. So that's why there is no Q branch, and also no odd rotational lines in the P and R branch transition. And here we can see there is a slight mismatch of energy that is accounted with the thermal energy, like compensated with a thermal energy relaxation. Now, this method, we need a ground, like we need to be carbon dioxide in 0 level again. But this transition, this is rapid vibration and relaxation, but this is very poor vibration and transition and relaxation. So most of the atoms, the carbon dioxide molecules, sorry, not atoms, carbon dioxide molecules disappear. So for this transition to happen very rapidly, we use helium to encounter this problem. So the helium has been found to be more effective in moving the vibrational energy from the carbon dioxide molecule and sending it back to the ground state. So the equation is like Z010 plus helium kinetic energy index of 000 plus helium kinetic energy. So that is why the carbon dioxide, nitrogen, and helium mixture in the carbon isotope is 1:1:8. unique range because the embryonic transition will involve additional transitions will involve C. Photons are involved. D is a vibrant laser. So electronic transitions, they are involved transition involves the energy 1 to 10 electron volt. Vibrational that give visible or impedance. Vibrational transitions involve the energy is 10 to the minus 2 electron volt, and that gives infrared. Rotational energy of transition involve almost 10 to the minus 4 electron volt, and that corresponds to microwave. So for infrared, the answer is vibrational transition and involved. That's what we did for it. Question 2. Energy involved is least for A. Vibrational transitions. B. Electronic transitions. C. Rotational transitions. D. All of the above. So as I mentioned, that rotational transitions has the least energy. So the answer is this, rotational transitions. Question 3. The spacing between adjacent vibrational levels in a molecule A gradually increases with increasing vibrational quantum number. B gradually decreases with increasing vibrational quantum number. C, they are equally spaced. D, none of the above. So know that the EHA is in basically vibration and energy level is denoted by mu plus half H mu naught, and mu naught plus that comes to H mu naught, independent of mu, so that they should be equally spaced. But that doesn't is the actual case scenario. Because this thing is not only that. It can go up to that has another term which denotes this. So for that reason, this doesn't have only this, it have some additional term. So for that reason, this was increasing. Oh, sorry. That it is evident that this is in minus, so the spacing reduces. So this is the answer. Zero-point energy first possible energy for a quantum oscillator. B exists on account of thermal energy. C independent of the frequency of the oscillation. D independent of the mass of the oscillator. So basically, 0-point energy is when mu is equal to 0. So E naught is half of H mu naught. E naught. So it's the lowest possible energy of the oscillator. And obviously, this is the independent of the frequency. It is not independent of the frequency of the oscillation. This is, we have frequency of the oscillation here. And this is K by mu. mu is ma and b by ma plus mb. So this is does not independent of the mass of the oscillator. This is also not. So the correct answer is this. And it is indeed the lowest possible energy level. Question 5. Consider two molecules of reduced masses m and 4m respectively. Assuming in the same spring constant K, what will be the ratio of the vibration energies for mu is equal to 1 vibration quantum number? I will directly deduce the answer writing the options. So basically, we know that mu naught is 1 by 2 pi root over k by mu, and E mu is mu plus half h mu naught. So for mu is equal to 1, that is 3 by 2 h mu. So that is basically 3 by 2 h cut upper mu. So E1 would be 3 by 2 h cut put over k mu1, and E2 would be 3 by 2 h cut k by mu. So E1 by E2 is basically mu2 by mu. So that is basically 4n by n, that is root 4, that is 4 by 1, that is 2 by 1, that is 2 is 2. So the answer is basically 2 is to 1. Question 6. The energy spacing between two rational levels of rotational levels of rotational quantum number J and J plus 2 is, I'll again calculate the thing and I'll put the answer. So I know EJ is J plus 1 to B. So for EJ plus 2 is J plus 2, J plus 3 into B, and EJ is J, basically. So EJ plus 2 minus EJ, which is delta E, would be B J plus 2 into J plus 3 minus B J into J plus 1. So B is common. This is J square plus 6 5J, and this is J square minus J. So that, and this is become 4J plus 6. So that is 2B 2J plus 3. This is the answer. Question number 7. Why is Q branch missing in carbon dioxide laser emission? Option A, even rotational numbers are missing in 001. Option B, all rotational numbers are missing in 001. Option C, carbon dioxide is symmetric molecule. Option D, carbon dioxide is a polar molecule. So we know this is true, that as even rotational numbers are missing in 001 and all rotational numbers are missing in 100 and 020, but that option is not here. But so why this is thing that even rotational numbers are not in 001 and what rotational numbers are missing in that, because that carbon dioxide is a symmetric molecule. That's why this thing happened. For that, delta J0 is not possible. That's why there is no Q branch. Now, let's discuss some questions. Force constant in molecule is 1870 Newton per meter. See of vibration of the molecule and spacing between its vibrational energy levels in electron volt. Given the mu carbon monoxide is 1.14 into 10 to the power minus 28 kilo. H is 6.626 into 10 to the power minus 27 arc second, and 1 electron volt is 1.60 into 10 to the power minus 12 arc. So we know mu naught. Mu naught or oscillation is 1 by 2 pi root over k by mu. Now if we put all this value here, we will get the power minus 28 kilo, but this comes to 6.45 into 10 to the power 30 per second or hertz. And the vibrational energy of the mu is h mu naught here, mu plus half. The separation between two successive vibrational energy level is delta U. We calculated h mu naught. We are not calculating that extra part, but for generally. So that is basically 6.63 into 10 to the power minus 27 into 6.45 into 10 to the power 13 second inverse, and that is R into second. So that gives us 42.76 into 10 to the power minus 14 arc, which is equivalent to 26 into 10 to the power minus 2 electron volt. It's 6.725 basically. So this is equal to 26 actually. 26, which is 26. Let's give that session. Question 9. Calculate the amplitude functions in the mu is equal to 0 level of the molecule omega, which has a stiff bond of 18.7 into 10 to the power 5 time per centimeter. So basically here K is 18.7 to 10 to the power 5 time per centimeter. Let x0 be the maximum displacement from the equilibrium position. So the potential energy at x is equal to x naught is equal to vibrational energy to the mu is equal to 0 state. So half of kx naught square is equal to half of h nu naught. So x naught is basically root over h nu naught by k. Mu naught is root over k mu into 1 by 2 pi. So mu for so this is question was for carbon monoxide. So mu for carbon monoxide is 12 into 16 into 6.023 into 10 to the power 23 whole square by 12 plus 16 plus 6.023 into 10 to the power 23, which is 1.14 into 10 to the power minus 26 kilo, which I've seen there. Mu naught is 1 by 2, 3.14 into 18.7 by 11.4 into 10 to the power minus 24. That would give you 6.45 into 10 to the power 13 second inverse. And when you put the thing here, x naught 6.63 into 10 to the power minus 27 into 6.45 into 10 to the power 13. by 18.7 into 10 to the power 5. You'll get the answer. That would be 4.78 into 10 to the power minus 10 centimeter, which is 4.78 into 10 to the power minus 2 angstrom. So these are kind of questions you can get in the quiz. That is for today. Thank you.